Chapter 6 is about what are called discrete random variables. This chapter 7 is going to be a continuation of these topics. There's like two sets of variables you can use, discrete and continuous. Chapter 6 will be about the discrete. Chapter 7 will be about continuous. What does that mean? A great question. Thank you so much for asking. Let's consider a probability experiment in which we flip a coin 2 times. The outcomes of the experiment are either heads, 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 tails, tails, heads, or tails, tails. Those are the 4 options you can, I know, I'm out of mints. 4 options you can have for flipping a coin 2 times. Rather than being interested in a particular outcome, like getting heads, heads, we might be interested in the number of heads. Like, I don't want any heads, I want 1 head, I want 2 heads. If the outcome of a probability experiment is a numerical result like this, numerical, we say the outcome is called a random variable. So here we go. Definition number 1 for this chapter. A random variable is a numerical measure of the outcome of a probability experiment, so its value is determined by chance. I want you to underline numerical measure. Random variables are typically denoted using capital letters such as X. So that is a capital letter on purpose. When you are defining my random variable, it needs to be a capital letter of whatever you are using, probably X. There are 2 types of random variables. Again, random variable is a numerical measure. Our first one, which is what we're going to focus on in this chapter, is called a discrete random variable. It has either a finite or a countable number of values. So underline the word countable there. The values of a discrete random variable can be plotted on a number line with space between each plot. So if you see this number line showing you a discrete random variable, you either have 0, then 1, then 2, then 3, then 4, but not the numbers in between them. So it's not continuous. On the other hand, a continuous random variable has infinitely many values. The values of a continuous random variable can be plotted on a line in an uninterrupted or continuous fashion. So see, this is a continuous random variable. You could have 0, 0.1, 0.2, 2.5, 3.75, all of the numbers in between these discrete numbers. Do you see the difference between discrete and continuous? Cool. So we're going to focus this chapter, chapter 6, on discrete random variables. Like I said, chapter 7 will catch up with our continuous random variables. But we can create probability distributions like we did in chapter 5 for these discrete random variable x's, provided the possible values of the random variable and their corresponding probabilities. We defined in chapter 5 a probability distribution to be correct if 2 things happened. And those same 2 things are going to be right here. This is going to be the same as chapter 5. The 2 rules in chapter 5 for something to be considered a probability distribution is that the sum of the probabilities had to equal 1. So the sum of probabilities equals 1. That's what this says. Sum of the probabilities, random variable x, is equal to 1. And our second rule in chapter 5, which still exists here, is that all of the probabilities of every variable you could get has to be between 0 and 1. 0 means it's an impossible event. 1 means that it's a certain event. And anywhere in between is the probability. If those 2 things are true, that the sum of all the probabilities in your discrete probability distribution add up to 1 and are between 0 and 1, then you do have a correct probability distribution. So for example, suppose we ask a basketball player to shoot 3 free throws. Let the random variable x represent the number of shots made. So either they could miss them all, so 0 made, they could make 1, they could make 2, or they could make 3. The table 1 here shows the probability distribution for random variable x. Here's some things I want you to notice. This is a capital letter on purpose. The random variable x is the number of shots made. These are little x's, though, on purpose. The options for big X, the number of shots made, is little x, 0, 1, 2, and 3. So we could go to little x's in tables to show the variations in my random variable, but we define it with a capital letter. We denote probabilities using the notation P of X, where P is a specific value of the random variable. We don't actually say P of X as you would in algebra. We actually read this as the probability that the random variable X equals X. So for example, this symbol right here, P of 3 equal to 0.51, is the probability that the random variable X equals 3 is 0.51. Or the probability that the number of shots made is 3 is 0.51. Okay? That's a probability distribution. Another thing we can do with probability distributions for discrete graphs is discrete probability distributions is we can graph them. Now, because they are discrete, there's going to be spaces in between them. So if you notice on this number line showing number of successful free throws, we have our plot at 0, we have our plot at 1, we have our plot at 2, and we have our plot at 3. They are not connected. They are discrete. When we are starting to describe these distributions, we started off just by talking about whether it was uniform or skewed. And in this case, this would be skewed to the left, because if we put like a cover on this, for lack of a better word, it would go out to the left, skewed left. But when we're now, as we're advancing in this class, when we describe the distribution of the variable, we need to describe not only its shape, but its center and spread as well. So the shape is easy skewed left. We will use the mean to talk about the center, and we will use the standard deviation to talk about the spread. So remember, those were the symbols, mu and sigma, for mean and standard deviation from chapter 3. So we're bringing all of that back together. So when it asks you to describe describe the distribution, you will tell me the shape of the curve, the center value, and the spread. So let's figure out how to do the mean and standard deviation for discrete random variables, because we have a new formula. Woo! The mean of a discrete random variable is given by the following formula. Notice that we have now a subscript on mu, and it's that capital letter X, telling us that this is the mean of a discrete random variable. That formula is as follows. The sum of the value of the random variable times the probability of observing the value of X. In other words, to find the mean of a discrete random variable, multiply each value of the random variable by its own probability and then add these products together. I do want to make sure you see this part down here, that we will follow the practice of rounding mean and standard deviation to one more decimal place than the values of the random variable itself. So for the most part, that means 1 decimal point, because we're going to generally see discrete random variables being whole numbers, but we'll see. So we're going to compute the mean of the discrete random variable given in table 1 from example 1. We're going to do this by hand first in the calculator, and then we'll go to Excel and make sure we remember how to do our Excel formulas. So to compute the mean, I've retyped the table for you. This is the table of those basketball players shooting free throws. If we're doing this by hand, this is the value of the random variable, and this is its probability. What is 0 times 0.01? 0. So this first one, I'm going to get 0. What is 1 times 0.10? 0.10. What is 2 times 0.38? 0.76. And then 3 times 0.51? All we need to do now is sum or add those numbers up. So 0 plus 0.10 plus 0.76 plus 1.53. We would get 2.39, but since we're following the practice of rounding to just 1 decimal place more than the value of the random variable, the value of my random variable are whole numbers. So how should I actually round this? 2.4 would be better, just to follow the practice. Obviously, if something tells you to round differently, you round differently, but that is generally what we're going to do. Shall we make sure we remember how to do this on Excel? Sure. Okay, open up your Excel. You've got your mouse and your number pad if you're going to use it. Let me pull mine up. Oops. All right, so I have my table there. Go ahead and type your table in if you did not. One of the practices I want to change for us using Excel, just because when you guys ask me for help, I have to like go through a whole process of figuring out what you've done. Please give me titles. So if you notice on mine on your screen, I have the same titles from the table, discrete random variable, values, and then the probability. Just, I make them bold because I'm extra, but if you could give me titles, that would be really helpful. That way, again, when I come to help you, I know what I'm looking at, and you remember what you're looking at. If we're doing this in Excel, what I need to do next column is multiply the value of the discrete random variable times the probability of the discrete random variable. So I'm going to do x times p of x. So just to show me what I'm doing, I'm going to go ahead and put that here so I can see what I'm doing. Now, in Excel, how do I get these two numbers to multiply together? What do I do? Equals. So I'm hitting the left arrow key twice to get to A2. And how do I tell it to multiply? Yeah, Shift 8. Unless you have a full keypad, in which case there's usually a multiply sign. And then I'm just going to hit the left keypad again to go to B2. I press enter. Now, what was the trick to get it to copy the formulas all the way down? Yeah, when it changes to the little skinny cross, boom, you can pull it down. It's going to copy paste your formulas all the way down. Again, a practice I want to change just because I think it would be helpful for me when I'm looking at your work. I want you to skip a row at the bottom of your table before we actually sum stuff so that I can see a title. And I want you to tell me that this is going to be the sum here. We are going to press equals, and we're going to type sum and open a set of parentheses. And with my fingers on the keypad, here's how you don't have to pick up the mouse again. I'm going to go up to the first one I want to be in my sum, and then I'm going to put a colon. So Shift semicolon puts a colon, and then I'm going to drag, or I'm going to type down, because see, it's going to extend. You see that how it's catching like the range of numbers? And then close the parentheses and press enter. Generally speaking, that goes a little faster than having to go with, especially if you don't have a mouse, to not have to take your hands off the keyboard. Really cool. Now, if you wanted to check it for rounding, you can make this round for you. Up here where it says number, you either have increased decimal or decreased decimal. So I want to decrease my decimals, and now it's rounding for me. Obviously, you can round that number on your own, but like, boom, we've just double checked our mean. Does all of that sound familiar to us? Mm-hmm. Okay, fabulous. Yeah, we were doing really well with Excel. I just want to clean that up. I would love titles, and I'd love a little space in between my table and when I start to do work, just so I can see what I'm looking at. Okay, cool. So we verified. What does this mean, though? What are we finding? And it's an interesting thing when it comes to discrete random variables. Our mean actually tells us a little bit more than it did in other problems. Suppose an experiment is repeated n independent times and the value of the random variable x is recorded. As the number of repetitions of the experiment increases, the sample mean value of the n trials will approach the mean of the random variable x. The difference between a sample mean and mu of x gets closer to 0 as n increases. This is a really fancy way of pointing out just literally this sentence right here. As the number of repetitions of a regular experiment increases, the sample mean of n trials will approach the mean of the random variable x. So if you do this trial a good number of times, over and over and over and over again, we can expect that our actual value we're going to get is going to be closer to that mean. So example 3, the basketball player from example 1 is asked to shoot 3 free throws 100 times. That's a significant number of times. Compute the mean number of free throws made. As the number of repetitions of the experiment increases, we expect the sample mean to get closer to 2.4, which is our mu. This becomes what's called an expected value of an experiment. So as we increase the number of times we've done an experiment, our mean also gets a new name. Our mean gets the name expected value. These are now interchangeable when it comes to discrete random variables. We can expect this to be our outcome. Because the mean of a random variable represents what we would expect to happen in the long run, it is also called, like I said, the expected value, capital E of capital X, the expected value of random variable X. The interpretation of expected value is the same as an interpretation of the mean for a discrete random variable. So this idea of discrete random variables giving us an expected mean allows us to do a little bit of light actuarial work, which is a field of mathematics that is used in insurance to determine like whether you would insure somebody, if it's a good insurance deal or a bad insurance deal. Here's a quick little example here to kind of get an idea of how this might work. Do y'all know how life insurance works? Do y'all know what life insurance is? Let's start at the beginning. Theoretically, so like if I have a life insurance policy, that means that I'm insuring what my life would be worth to my beneficiary with these like monthly payments. So like let's say I had, I don't know, I don't have kids, but let's say I had a kid and they were my beneficiary. If I die, the insurance company is going to pay my child, my beneficiary, this sum of money that I started to pay into, but it's a life insurance policy to like put them in a good spot, okay? That's how life insurance, really simple, how it works. So here's an example. A term life insurance policy will pay a beneficiary, that's the person who gets the money, a certain sum of money upon the death of the policyholder. These policies have premiums, that's like a monthly payment, premiums that must be paid annually. Suppose an 18-year-old male buys a $250,000 one-year term life insurance policy for $350. According to the National Vital Statistics Report, Volume 58, Number 21, the probability that the male will survive the year is 0.998937. Compute the expected value of this policy to the insurance company. There's a lot of things that are going to happen in this problem. First thing is we need to determine if this represents a discrete random variable. What are the two options for the 18-year-old male? He's either going to live or he's going to die. So we have two options. We have an option that the man survives, and we have an option that the man dies. If the man survives, how much money will the insurance company make off of this man? How much did he pay into the insurance policy? Yeah. So if he survives, the insurance company makes $350 because he paid for this thing and he didn't need a cash out because he stayed alive. If he dies, though, how much is the insurance company going to have to pay his beneficiary? But he already paid $350 of it, so we're going to subtract it. So if we do $250,000 minus the $350 that the guy already paid the insurance company, so they're plus that money already. How much money, I guess I should say it like this, would the insurance company lose if they have to pay out his term life and policy? Yeah, so they would pay negative $249,650. So if the man survives, the insurance company is making money. If he dies, they're having to pay that out. They also told us that the probability that the male will survive, so this option, the probability that the insurance company would have to pay, would earn $350 because the guy survived, would be 0.998937, and after lunch, we will deal with the rest of this problem. Okay, now that we're back from lunch, let's think of what the probability would be for the not survival. But if we think about it, this is kind of like a binary situation where there's either he survives or he dies. So if the probability that he survives is this, how would I find the probability that he dies? 1 minus. This is the complement. If he's not surviving, he's dying. So they are complements of each other, which means we can find that the probability that the man would die would be 0.001063. How did we get this number? We did 1 minus 0.998937. That's how we got that number. We'll go ahead and do this with our calculator since these numbers there's not a ton of data here. But if we're going to find the expected value, we just need to find the mean of this random variable. So we are going to multiply x times the probability of x for both him surviving and him dying. The probability that he survives times the money it would cost the insurance company if he survived. Actually, they would earn this. I said that backwards. If we multiply those two things, we would get 349.62795. And this is still money. If we do the money that the insurance company would have to pay out if he dies, times the probability that that happens, that would end up being, if you trust me, negative 265.37795. And since our formula for the mean of this simple random variable is literally just the sum of these two things, all we're going to do is add those two numbers together. And if you trust me, this ends up being $84.25. So a company decides their premiums or how much their life insurance or their insurance things cost based on something like this. It's called actuarial work. It's a whole branch of mathematics. Because the company that sold this man his life insurance policy expects to make $84.25 for each 18-year-old male client it insures. Because they're going to bank on a lot of them surviving. So they have this cost of $350 to make up for the ones that don't survive and the ones that they have to pay out the money for. But they should still expect to make that much money per male client. That's how insurance companies decide their premiums, based on your age and the probabilities of the things happening that they're insuring against. Obviously, we could have done this in Excel, right? So later on when you're doing these problems, you can do this in Excel. That's the mean, which is also the expected value. The second way we're going to describe these distributions is, again, with the spread. So we do that with standard deviation. We find the standard deviation of a discrete random variable x given by this formula. Notice again that we have sigma now with a subscript of capital X, meaning it is the sigma of that simple random variable. We're going to use this formula, which if we look from the insides out, we're going to have to start by looking at the insides of the insides of the insides. We're going to subtract the mean from the value of the random variable. We're then going to square that. We're then going to multiply that by the probability, and then we're going to sum all of those things up and take the square root. Work from the inside out. We'll do this one by hand, and then we'll go to Excel, make sure we still remember how to do that. So I recopied the table. This is the shooting basketballs example. We're still here. We need to know the mean, which we found. By the way, we're going to use the unrounded mean, so 2.39 for this problem, just to be a little bit more accurate. So if we do the expected value 0, not expected value, the value of the random variable 0 minus 2.39, we're going to get negative 2.39. If we do 1 minus 2.39, we're going to get negative 1.39. Value of the random variable is 2 minus 2.39, negative 0.39. And 3 minus 2.39, 0.61. That is the difference between the value of the random variable and the mean. We're then going to square all of those numbers. So if you trust me to square all of these numbers like you would in your calculator, make sure you use parentheses if you're doing this, because negative times negative is positive. So all of this whole column should be positive. You're welcome. If we square those numbers, it's 5.7121 and then 1.9321 and then 0.1521 and 0.3721. So we have the sum of the difference between the expected value. Sorry, we have the square of the difference between the expected value and mu. Not expected value, I keep saying that. value of the random variable. Then we're going to take these columns, this squared term, and we're going to multiply it by the probability. So we're going to do 5.7121 times 0.01. You should get 0.057121. And again, you're going to multiply the sum of the difference times the probability, that next column or next row, and on and on. Okay, honestly, I cannot read my handwriting on this one. What is the number for the third row? 0.057798 or 88? 98. And then 0.189771. So we have all of those values for each of the values of the random variable. We then sum those values. We would get 0.4979. And then following the formula, we take the square root of that to get that our standard deviation is 0.7056. Or if we're reporting this to how we said we should, how would we report this number? One more decimal than the value of the random variable. Value of the random variables are all whole numbers, so we would report this as 0.7. So we have the mean, 2.4. We have the standard deviation, 0.7. And based on the graph, we knew that the shape of the graph is skewed left. Those are the ways you're describing this random variable. One last thing here, remember that the variance of a discrete random variable is the value underneath the square root in the computation of standard deviation. So if you're asked for the variance, you want this number. That is the variance. So the variance of the discrete random variable in example 1, which is a squared value, sigma squared, is 0.4979. Do y'all want to do this one together in Excel just to make sure we still remember how to do all of these formulas and to kind of clean up? Remember, I'm wanting headers and all that stuff to see what I'm looking for. Okay, so you should already have your table typed in because it's the same exact table from the example before. Yes. I'm going to leave this column here because it's how we found the sum, or that was the mean. But I'm going to go ahead and make a new part of this table. I'm skipping a column just because it's a new idea for me. This first one, I need x minus mu. So in this column, I'm going to press equals, and I'm going to highlight the x column, and I'm going to subtract mu, which we found in C7. And then remember, I haven't touched my mouse once. I'm only using the keypad, which might be easier for you guys if you're not using a mouse. However, if I drag...
What is the formula that you wrote?
Oh, thank you so much. It's x minus mu with a subscript of x. It looks gnarly on Excel because it doesn't actually make it a subscript. And I guess this should be a capital X if I'm really being picky. If I took this one and dragged it down, though, it would change the value of the C7 to go down just as much as it's moving the other ones down. So I don't want that. Instead, what I'm going to do, and this is a shortcut for you now that we have a little bit of Excel work, we're going to freeze C7. Meaning, when I go into the formula for C7, you can't see it, it's up here, it's very small, so sorry, up here. I'm going to put a $sign before the C and a $sign before the 7. That's the indicator for Excel that you are freezing that cell. Don't change this one. I'll start over.
Okay.
Okay. So I said equals x, so 0, right? A2, minus your mean, which we found earlier. But if I press enter and try to drag that down, it's going to change C7 just like it's changing A2. So we want C7 to be sticky, to freeze it. What you do, sorry, I'm like banging back here. We go in front of the C, and we put a $sign, and in front of the 7, and we put a $sign. And it's going to freeze that selection at C7. So now when I go to drag, notice it's going to leave C7 in my formula. Now it's A3 minus C7. This one is A4 minus C7. And then A5 minus C7. It has frozen C7. Didn't change that one when you dragged it down. It's a helpful Excel tip there. Then I'm going to square that term. How do I square something in Excel? Shift 6 and then put a 2. Very good. So we're going to square it. Boom. So we're still working from the inside out. We're going to then multiply by the probability of x. Let me make sure you can see my titles. So I'm going to take this value and I'm going to multiply it by the probability. We pull that down. Times the probability. We then do the sum of that last column that's times p of x, which we would do equals the sum of, shortcut so you don't have to pick up your mouse. With my keypad, I go up, 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 up till I'm at the top, colon, and then pull it down. You can also pick up your mouse if you're like, I'm over this, Miss Quigley. Yes, sorry.
What was the formula for the time?
It's great question. So sorry, I went kind of fast. It is this cell times the probability. This is why the titles will be helpful. So it's x minus mu of x, square that term, multiply by p of x. So I have the sum, and then all we need after that is the square root so I can find sigma.
I have no idea what happened.
You pressed page down, I think. Look for your page up button.
Where is that?
It's on your keypad.
No, it's in like 4 billion something something. Oh my god, what the hell?
A disaster.
Okay.
Sorry, square root. How do we do the square root? I guess I kind of already showed you. What's the letters for square root? SQRT, open parentheses, and then highlight the cell you want to take the square root of. And then boom. We have our value, and you can change it to let it round for you, or that's a pretty obvious rounding. Oh, I left this on this whole time.